Chem activity number 19 and the corresponding videos, we will explore the Bohr model of the hydrogen atom. To set the stage, let's go back to around 1911. Ernest Rutherford and his colleagues had proposed a model of the atom, where there was a highly massive region, positively charged at the core of the atom, and then outside of that, there would be an electron which would be negatively charged. Now the drawing in front of you represents the hydrogen atom, and it's not to scale at all, because the proposal by Rutherford was that there's a huge distance between the nuclear region, the positively charged region, and where the electron is found. But if we drew it to scale, then you wouldn't be able to see both particles in one drawing. Now the idea is that the positive nucleus attracted the negatively charged particle, and as such, the idea is that the electron would not escape. It would be attracted to that positively charged particle. But there's a serious problem with this model, and the serious problem had to do with classic electrostatic theory at the time. The negatively charged particle would be circling the positively charged nucleus, and as such, that circular motion involves an acceleration. A negatively charged particle accelerating would lose energy, according to classical physics. If it loses energy, that negatively charged particle should collapse and collide with the nucleus. And so, while the model had some supporting evidence based on the gold foil experiment, there were flaws with this model. And of course, this was a concern to scientists at the time. Along came Niels Bohr. Niels Bohr had just gotten his PhD. He was around 26 years old, a young man ready to tackle the world of physics and chemistry. And he had a solution for the Rutherford model. In fact, he went to work with Rutherford in Cambridge and proposed the following very dramatic idea. Niels Bohr simply said classical physics does not apply at the atomic level. So he had different ideas about how the atom would be organized. That was a very bold statement by a 26-year-old, in a sense, combating 300, 400 years of classical physics and saying they don't apply at the atomic level. Now, let's look at a little bit of a simulation so you might have a sense of what Niels Bohr was in fact suggesting. So in this simulation, first of all, you may notice that you've got a positively charged particle, that would be our proton in the nucleus, and the negatively charged electron. And again, that negatively charged electron, because it's accelerating, should be losing energy and would collapse into the nucleus. Niels Bohr, of course, said no, classical physics does not apply, and therefore this electron does not go collapsing into the nucleus. So we're going to take a look at it from a different vantage point. So here again is this negatively charged electron circling the positively charged nucleus. Again, this is not to scale at all. There'd be huge distance between those two particles. So Niels Bohr said this was ground state. This was an allowed energy state of that electron. And there would be other allowed energy states. Only certain energy states would be allowed. He did some mathematical calculations for what would keep the electron in the atom, and also what would be other energy states where the electron could exist. And so he argued that energy could be absorbed by the atom, and the electron would be excited to a higher energy state. We'll see this as the electron now will suddenly move to an outer energy level because the atom has absorbed energy. So now the electron's at a higher state. Now you didn't see it move there. It just suddenly is at a higher state, and then it will lose that energy because it has to come back down to ground state. There it gained energy again, and then suddenly it will just lose energy by emitting light. It just gained energy again, and then the electron loses energy and comes back down to ground state. So Niels Bohr said that the electron would spend most of its time in ground state, but energy could be absorbed such that it would rise to a higher energy state. Now, so you get to see a difference between what more classical physics might say Generally, if energy is absorbed, it would be thought to be more continuous, like accelerating in a car, and energy would be lost more continuously. So picture you put the foot on the pedal and the car speeds up. And so gradually it speeds up, goes faster and faster, and then slows down, decelerates. But what Niels Bohr is proposing is that an electron would absorb energy in discrete amounts of energy, and only those energy states would be allowed. So now the electron's at a higher energy state, and then it loses that energy, and suddenly it's back down to ground state. There are no intermediate energy states. Absorbed energy, and then loses that energy. Now I just paused the animation here, and just to remind you that Niels Bohr did the appropriate mathematical calculations for what those different energy states would be, and that gave credence to his incredible proposal. So let's take a look now in the actual notes. This diagram essentially gives a symbolic representation or a schematic representation of the animation that you just saw. So the original work that Bohr did was essentially with the hydrogen atom. His model was then adapted to other atoms, but it works best with the hydrogen atom. The idea is that we have our proton, single proton for the hydrogen atom in the nucleus, and we have electron at a certain distance. Of course, it's a huge distance, relatively speaking, and this would be the lowest energy state. The electron would spend most of its time in that state. And as I say, Niels Bohr made some calculations about what would be the appropriate energy to keep, in a sense, that electron in orbit around the nucleus. Now, I say in orbit somewhat reluctantly, because we'll see later on that that's not really the best description. Niels Bohr also did some calculations as to what would be other allowed energy states. So let us say that starting from ground state, energy is absorbed, and what would happen here is the electron would be bumped up to a higher energy state. As I say, only discrete energy states would be allowed. Now, the energy can come from a variety of sources. So, for instance, the energy can come from light, the energy can come from heating, and it also can come from an electrical source. And that would bump up the electron to a higher energy state. But the issue is that that's an unstable state. So just like what we saw in the simulation, the electron would temporarily be in that state, but then the electron would fall back down. Now I say fall back down, it's not falling in the true sense of, think of something falling off a cliff, because we never see the electron in an intermediate state. It's either at 2 or 3 or 1. So if it's up at 3 and then suddenly it's back down at 1. When it does this, energy is lost. So the pathway downwards involves a loss of energy. So let's just make clear here, energy lost. And as it turns out, energy is essentially lost by light. The fact that energy is lost by light allowed Bohr to actually, in a sense, test his theory, because he could look for wavelengths or frequencies of light that would correspond to the difference in energy of these different energy states. So going down, energy is lost. Maybe to make clear, in case it wasn't clear, in the going up to the higher energy state, that's a gain of energy. So we're at a stable state, energy is gained, it brings us up to a higher energy state, which is less stable. The electron in that higher energy state will eventually lose that energy, or we could say the atom returns to ground state and that energy is lost as light. Finally, there's an extreme situation, for instance, and that extreme situation would be if the electron starting at, let's say, ground state, or actually in any of the excited states, the electron is brought to infinity. Now, of course, infinity is hard to imagine, but in a sense, the electron is brought to a position where it is essentially outside of the atom. So infinity, you can think of outside of atom, or removal from atom. And the idea is that therefore we would be left with a single proton with its positive charge. Single proton with a positive charge is known as an ion, or of course it's known as a cation. And you might imagine that the energy required to do this can be called the ionization energy. You will see later that we'll be talking about ionization energies in terms of trends in the periodic table. So to review again, the atom spends most of its time in ground state, where the electron is in the first energy level, n equal to 1. The atom can then absorb energy, receive energy, either in the form of light, heat, electrical energy, and what this does is it bumps up the electron to higher energy states. This is an unstable state, so the electron, when coming back down to ground state, will lose energy. This energy is lost as light. Now, I say the electron loses energy. It's maybe better to be thinking that the atom itself is losing energy, and now the atom returns down to a more stable state. Finally, it's possible actually to supply sufficient energy that the electron is bumped completely out of the atom, and we would call that the ionization energy.